Okay, so yesterday we talked about convexity, and we ended with the notion of strong convexity. So today we are going to use those knowledge, and we are going to tackle first the notion of weak convergence. After this notion of weak convergence, well, only weak here, but we will talk about weak convergence. And after that, we will talk about fixed point theory a little bit. Just the part that will be useful for convex analysis. And finally, we will apply this fixed point theory into the theory of convex analysis to study first convex minimization, and second, the problem that I am interested in, which is called a convex feasibility problem. Okay, and we will mainly be in cat0 space for the fixed point theory and for the convex optimization. And if we have time, I don't know, if we have time, I will talk a little bit about cat-kappa space. What's the difference? Okay, so weak convergence. So we want to define a weak convergence, and okay, suppose, as always, suppose always that xd is a complete let's not say always, because later we will talk about cat0. So cat-kappa space such that the diameter of x is strictly less than the kappa over 2. Okay. So if kappa is positive, then we have this restriction, the diameter condition. If it's not, then we don't have anything. I mean, we don't have any restriction. Okay, next we are going to define what it means for weak convergence in the space of, in the cat-kappa space. Remember that a Hilbert space is an example, is one example of a cat-kappa space. Therefore, this kind of space can be of infinite dimensional. And in that case, strong convergence or strong topology is not the best choice. Okay, so we want to come up with an alternative version of, okay, in linear space you have the weak topology, but here you don't have the weak topology. Okay, at least how we first came to this, we don't approach this via topology. We define an analytical version of convergence, and we call this a weak convergence because this notion will be equivalent to the weak convergence in Hilbert spaces. So let me give you the definition. So we start with the bounded sequence. Bounded sequence xn, of course, in X. We said that this sequence is weakly convergent to some points, to a point X in X if okay, so we would like to say this: if X is the unique common minimizer the function r dot un for every subset, no, not subset, subsequence un of xn. So this sentence first, and then I will define what this notion is. So x is let's say the weak limit of this bounded sequence. What does it mean? It means that this x has to be a unique common minimizer of this function, okay, r dot un. The inputs comes into the dot, okay. It's a unique minimizer for this function for every subsequence un of xn. So this function, you have one input, but actually it was parameterized by un. And what is un? Un is a subsequence of xn, okay. You vary the subsequence un, okay, all the possible ways, then you will get this function and you minimize this function, okay. And x here have to be the unique minimizer of this function for every subsequence un that parameterize this this function r dot un. And what is r dot un? Okay, so if you put, let me call u here. If we put u here, these functions will return the value lim sup as n tends to infinity of distance between u and un squared. Okay, so this is the definition of r u un. So if you change the value of if you change the point u here, u will comes into this and you compute the lim sup with un fixed. Okay, you compute, and this will return you a non-negative real number, and you find the point u which minimizes this quantity. Okay, the point that minimizes this quantity have to be x, and it has to be x for every possible subsequence un here. So so here, in order to guarantee that this definition is well defined, we have to take into account the strong convexity of the distance squared function. Okay. So for each n, you will see that d dot un squared is a strongly convex function, as we talked about yesterday, right? We are in what? We are in complete kappa space with diameter condition if kappa is positive. Okay, so within this condition, we know that the distance squared to any fixed point will be strongly convex. And again, from yesterday, we have like a result stated in an example that if you have a sequence of strongly convex functions with the same modulus, then you can take the lim sup, and that lim sup will still be strongly convex. Okay, and the last result of yesterday states that if you have a strongly convex function which is lower semi-continuous 2, then that function will have a unique minimizer. Okay, so here is where this result comes in, because this is a sequence of strongly convex functions. You take the lim sup, this thing which is called r dot un is therefore a strongly convex function with modulus equals to c kappa if kappa is positive, and it's equals to 1 if kappa is less than or equals to 0. So this R dot un is a strongly convex function defined on a complete Kappa space with this condition. Therefore, it has a unique minimizer. Okay, so saying that x is the unique common minimizer of this function parameterized by the subsequence un is it's not artificial. It can happen. So the problem reduces to the question of whether or not x is the unique common minimizer. Okay, you don't have to ask about existence of the minimizer because we can use the results yesterday to guarantee that fact. Right. Okay, so this is the definition of weak convergence when we are in Kappa space. Okay. So for consistency, I will state this proposition. Okay. Or more like a remark, I think. Let's call it a remark. If X is a Hilbert space, then the weak convergence in the previous definition coincides with the classical weak convergence. So more like a remark, but you have to prove, of course. Let's go back to this a little bit. I will give you a reference. So this definition was first defined in 2008 by Kirk. Okay, William R. Kirk and Bancha Panyanak in 2008. Okay, this is for cat 0 case. So at first it was defined for kappa equals to 0, and then it was extended in 2009 by Espinola and Fernandez Leon. Okay, just to give you the proper references to this definition. Okay, so what do we need to know about the weak convergence? We need this theorem. It states like this: every bounded sequence in X has a weakly convergent subsequence okay. And one more note. Actually, it's kind of trivial, but I will note it. That, okay, if you have a sequence xn and this sequence xn weakly converges or is weakly convergent to a point x, then this weak limit is unique. Okay, you cannot have two. The fact that it is unique follows directly from the fact that this function is strongly convex, and hence it has a unique minimizer. Okay, and so you cannot have two weak limits. Okay, it's kind of trivial, but just to note to you in the case you didn't notice. Okay, and this is a more important one. Okay, every bounded sequence in X has a weakly convergent subsequence. Okay, this is important. This is like the situation when you're in a Hilbert space, or more generally in a reflexive Banach space. Okay, so in such a space you can have this kind of subsequential property. And you have to notice a little bit that for kappa positive it's not always working. We have to induce this kind of property. Okay, or at least the diameter of the sequence have to be less than d kappa over 2. If the space is large, let's say you don't want to encage yourself to a small diameter, and you want to work on a space which is the diameter can be larger, you can, but if you want to guarantee that a sequence has a weakly convergent subsequence, then at least that sequence has to be contained in a cat kappa subspace with this kind of diameter. Or indirectly you can say that the diameter of the set of points in the sequence has diameter less than d kappa over 2. So that's an alternative way to do that. If you want to live in a larger space, there is no real gain for that, because most of the theory in cat kappa space when kappa is positive is restricted within this kind of condition. It can be relaxed just a little bit, but most of the time you will require this property. I will note that there is okay, so before I note, I have to state why we need this property, because we need the convexity of the distance. We need, yeah, that's the main thing, and what comes after this mainly follows because we need the convexity of the distance. But recently there is one paper in Archive 2021. I do not remember the full list of authors, but one of them are General Lopez. I cannot remember the full list of authors, but they cleverly come up with a nice result, and their approach is kind of natural. So if you cannot get a convex, if you cannot get something convex, then work with something non-convex. Use the non-convex approach. It's very, very direct, but of course it's very difficult to get over these difficulties that arise when you don't have the convexity, especially in this kind of space. Okay, so that's all the results that you need to know regarding the weak convergence. It's a mode of convergence which is weaker than convergence in the metric. You can notice that if xn converges in the metric or strongly to the point x, then of course this lim sub will always be 0, and hence the strong limit will always be the minimizer of this for every subsequence, and therefore if you have a strongly convergent sequence, then it is weakly convergent as well to the same limit. One fun fact: even though this was introduced back in 2008, 2009, it was introduced analytically like this. You construct using a sequence, you minimize. The approach is very analytical. It's not topological approach. Okay, so one natural question arises: can we construct a topology on X for which the convergence in such a topology coincide with this weak convergence. It has been open for a long time until earlier this year. There was a paper by Anton Petunin who solved this question, who solved this open problem affirmatively. So there is a topology for which the convergence in that topology coincides with this. Okay, and that's a kind of surprise because earlier there were some attempts and we can partially solve this affirmatively, but okay, so this guy Anton Petunin decided he can do better. Okay, so that's a little story regarding this kind of weak convergence. Then we will enter into the study of fixed point theory. Okay, so this is the main theme today. We want to study fixed point theory and relate some results, some fixed point results to convex analysis. Okay, and as I said, I will treat this in kappa equals to or less than 0 first, and if we still have time, I don't expect we have too much time, but if we have time, okay, we will enter the situation when kappa is positive, and you can see that they are completely different. You have to use different tools to solve the same problem. Okay, so I will introduce you to some notions from fixed point theory first, and then I will apply it to convex analysis. So, given a metric space M D, so I will use M because I will reserve X for the cat kappa space, or in our case, I might be cat 0 space, but for general metric space, I will use M, okay? So given a metric space M and a map T defined on M into itself, okay? A point X bar in M is called a fixed point of T if you map this point X bar under the map T, and the result you get is still X bar. So that is why you call it a fixed point, because the value is not changing. It's fixed by the map T. Okay, and to study the existence and the approximation of a fixed point for a given map T, you will need to know some classes of maps first. So we have a map T, M to M, just like that. Okay, just like that I define over here. Okay, here just any metric. Actually, if to define a fixed point, you don't need a metric space. You can come up with any set, but we will not do anything without metric structure. So for here, I assume that M is a metric space. Okay. Okay, and the map T from a metric space M into itself is said to be, first, it's said to be a contraction. If there exists a constant k belongs to the interval 0 to 1. You can include 0 if you want, but there's no real gain here. Okay, let's include. So if there exists k belongs to this interval such that distance between t of x and t of y is less than or equals to k times the distance between x and y for every x and y belonging to M. Okay, so when you have a point x here and y here, you map x into tx, you map y into ty. Okay, the distance between x and y and the distance between tx and ty are measured, and the distance between the values here must be less than or equals to a factor k, which is less than 1, times x and y. So we call it a contraction because we have to contract this distance by some parameter k, okay, by some factor k. So it have to really contract. Okay, so distance between tx and ty cannot be equals to the distance between x and y. It has to contract. So it shrinks down the distance by the factor of k. Secondly, we say that T is non-expansive if distance between T of x and T of y is less than or equals to the distance between x and y for every x and y belonging to M. So this is a kind of relaxed version of a contraction, because the contraction asks you that the distance after it maps x and y into tx and ty, this distance has to be contract. It has to shrink. Okay, so it has to be strictly less than this, but not only strictly, it has to decrease by the factor of k. But the non-expansivity just asks you that the distance between 2 points after being mapped by t is not expansive, it's not being larger than the distance between mapping, before mapping, sorry, the distance between x, y before it was mapped. So if you draw, tx and ty can have the same distance of x and y, okay? And okay, we have an even weaker one, which is called a quasi-non-expansive map. Okay, it asks you two things. First thing, the fixed point of quasi-non-expansive map has to exist. So fixed point of T must not be empty. And for any let me write down the inequality first. Distance between Tx and U is not larger than distance between x and u. Okay, and this we have for every x in M and every u in fixed T. Okay, so it's kind of non-expansive map. Okay, it's kind of similar, but with one restriction, more relaxed condition, is that the point y that you take here, in order to satisfy this inequality, you don't need to take for every y, you can just take any fixed point. Okay, so if you fix a fixed point of t and you map another point x, the map t will bring this point x closer to the fixed point z. Okay, and I think I have to write here a little bit, because we use fixed t, but I did not write formally what it is. So fixed t is the set of fixed points. That is, it is the set of x in M such that t of x is equals to x. Okay, just a set of fixed points. Okay, and these are three types of maps that we work with a lot in fixed point theory. There are a lot of generalizations, but for our applications, for our purpose, I don't think we need more. We need some strengthened version of these notions, but not more generalized. No, we want to be more specific. We are going in the opposite way. Okay, so the strongest result is, okay, the strongest notion is the contraction. The weaker one is the non-expansivity, and the weakest for now is the quasi-non-expansivity. Let's see what we can do with them. Okay, let me recall a very well-known theorem, which is called the Banach's contraction principle. Banach's contraction principle, named after Stefan Banach, of course. Banach himself proposed this results for solving Cauchy problems, ODE, in his thesis in 1922. And by the way, next year we may celebrate a 100 year of Banach contraction principle. Okay, so what does it say? It says like this. So let MD be a complete metric space Okay, let MD be a complete metric space. T M to M. is a contraction. Then we have two conclusions. Actually, we can have more, but the one that I will address are two items. The first one, T has a unique fixed point. Okay, existence and uniqueness result. Very nice. Let's call this unique fixed point x star. No, x bar. And secondly, if we take any x naught randomly from M, the Picard sequence a Picard sequence is defined by, okay, we don't need to write this long. I will just contract it. T n x naught. T to the power of n here means T to the power of n. This is n times iterations of T. So you compose this map T n times and apply it to the point x naught. Okay. And this Picard sequence, of course, the sequence is on n, is convergent to x bar. Okay, so this is a very nice result. Why? Because firstly, you have existence and uniqueness of a fixed point of this map T. And secondly, not only you can show that it exists and it's unique, you have a constructive way to construct this x bar, that is by taking this Picard sequence. Okay, so you keep iterating this sequence until, well, sufficiently large n, you will get very, very close to x bar. Actually, you have an estimation of the arrows of the distance of this to x bar as well, but that is not of importance right now. So if you are interested, please look up in the literature. You will see the estimation of the distance between T and x naught to x bar. Okay. Okay, so this is the ideal case. The approximation method by Picard sequence is defined very easily. You just keep, you first compute x naught, and then you take x naught inside of T. Maybe I should add a parenthesis here, and then you just apply another T. Okay, and this is T2 x naught, and you keep doing this. You will converge to the solution. Okay, this is very constructive, and the construction is very, very simple. Now we want to know that, okay, we have this when you have a contraction. How about when you have a non-expansive? Will you get this? The answer is no. We can construct a very simple example of a non-expansive map. Okay, suppose this is R2, and you are considering this is the unit ball, so center at 0, 0 and radius 1. Okay, this is M, and then you consider actually you can take the whole space. You don't have to restrict to this unit ball, but you can if you'd like. And then the mapping is defined by the rotation. If you take a point X anywhere in this set, you rotate it by, let's say, 90 degrees. Okay, so this is X. You rotate by 90 degrees. Here you have T of X. Okay, so what is the fixed point of this? The fixed point of this is 0. I mean 0, 0, the origin. This is the fixed point because when you apply the rotation, it doesn't rotate anywhere. It just stays there. But for other points, when you do the rotation, it rotates. It will not stay fixed. Okay? Okay, and what happens when you take, for example, if you take x naught to be this point, you apply the rotation one time, you get this point, you rotate it by 90 degrees. And then you take this and you apply it into another rotation by 90 degrees, you get this point, right? Another time you get this, and then you come back to x. None of these 4 points are fixed point, but if you keep doing the Picard's iteration for this start point x, you will jump cyclically between these 4 points. And that is not a fixed point. Okay, so for this example, T has a unique fixed point, yes, which is 0, but the Picard sequence is not convergent. Okay, it's not convergent. And if you take the subsequence, still not convergent. Okay, there is a convergent subsequence, but it's not a fixed point anyway. Okay, so and one more thing, the rotation by 90 degrees is a non-expansive map, because if you take 2 points, let's say I take these 2 points, I rotate these 2 points by 90 degrees. The distance between the 2 points after and before the rotations are the same. You didn't change the distance between the 2 points. Okay, so that's good. Let me bring this example to another level. So I delete all the points inside. I have this. This is unit sphere, S1. Okay, and I define everything in the same way. T is rotation by 90 degrees, but on S1. What is S1 here? S1 here is complete, of course. T here, T which is the rotation, is a non-expansive. So you have a non-expansive map defined on a complete metric space, but see, every point on here, it rotates. It's not fixed. So T is a non-expansive map on a complete metric space does not mean that you will have the existence of a fixed point. In this example, you don't have a fixed point. Okay? So number 2 cannot come because you have a fixed point x bar here, but this point does not exist, so we don't speak of the number 2. Number 1 is not hold. So things can be very complicated when you talk about when you talk about non-expansive maps. Okay, you have to induce conditions. Sorry, you have to impose conditions, not induce. Okay, so what should we do when we want to deal with non-expansive maps? In Hilbert space, there were some attempts long time ago in the 50s there were results like of Kirk's, of Browder, and so on. They try to come up with the existence theorem and how to approximate the fixed point when the map T is non-expansive. Okay, the result is impressive, but we are not going to talk about them today. We are going to talk about an equivalent version in Kappa space. Okay, why didn't I erase this? Let's have a theorem. Now we come back to x, and x is okay, complete. Kappa space. With diameter of x less than d kappa over 2. And you have a map T from C into C. No, I have to define C first. Complete Kappa space. C subset of X is non-empty, closed and convex. T is defined from C into C, is non-expansive. Okay. Then we somehow make use of the contraction principle of Banach's. Okay, what Banach says is that when T is a contraction, you have a unique fixed point, and you can approximate this unique fixed point by using the Picard situation or Picard sequence. Here you do things quite similarly. You go through the fixed point of a contraction. Okay, so instead of consider the map T, you construct another map. Okay, so you have the map T here, coming from that, which is non-expansive, and you have not ID. Sorry, here is Z. Okay, I was thinking about other things. Okay, you fix any Z here, you take any lambda, then the map here, you put your input here in the map T, and then you make a combination, a convex combination between the point Z. Then this map is a contraction. So since this is a contraction, it has a unique fixed point. where we will denote by x lambda, and this is in C, of course, because the domain is C. Okay, C is non-empty closed convex. You have C being a complete metric space, subspace of X, and this is a map on C, which is a contraction, so you can guarantee using the Banach contraction principle that this averaging has a unique fixed point where we denote the unique fixed point with x lambda. What's next? So now you want to take limit as n tends to infinity of the point x with lambda equals to 1 over n plus 1. Okay. If you take the limit as n tends to infinity, then you have the distance between x of I over n plus 1 and the map t at this same point tends to 0. Okay, x1 over n plus 1 is the fixed point of this map when lambda equals to 1 over n plus 1. Okay, you compare the value, the point and the value, and it will converge to 0. That means as you increase the number n, the integer n, the point x at 1 over n plus 1 is becoming closer and closer to the property of a fixed point, because this will converge to 0, or I can roughly say that this point is an approximate fixed point sequence. And finally, no, not finally, almost finally, you can show that x1 over n plus 1, if consider this as a sequence, this has a weakly convergent subsequence. Okay, so this is almost the rough proof of this theorem. Okay, so you have this kind of sequence, and then you can extract from this sequence a weakly convergent subsequence, and we call the limit of this weakly convergent subsequence z. Oh no, not a good one, because you used z there. So let's call this another thing. Let's call this x bar. And finally, when we have that x bar, we show that x bar actually belongs to the fixed point set of T. Okay, so this is kind of a proof step that you use in order to show that when you have a non-expansive map defined on a non-empty closed and convex subset of a complete ket-kappa space with this kind of condition, then this map, this non-expansive map, will have at least one fixed point. Okay, and the proof is not so difficult. The fact that this one is a contraction comes easily. You know that the distance on this space is convex, so you can just compute the distance between this map at x and at y. You compare, you use the convexity of the distance. You get that this one is a contraction with the contraction parameter k equals to lambda. Okay, after that, what do? You extract its unique fixed point. You call it x lambda. Then you show that x, when lambda equals to 1 over n plus 1, this sequence is an approximate fixed point sequence. So this thing converges to 0. And from this kind of fact, you will somehow be able to show that this sequence is bounded sequence. So as it is a bounded sequence, we can take a weakly convergent subsequence, right? I think we wrote it a word or two ago. So I think it's over here. It was over here. That every bounded sequence in this space has a weakly convergent subsequence. So you extract that weakly convergent subsequence and you have a limit x bar. Now you use there is an additional step to show that x bar is a fixed point. It's not difficult. So now you have the existence result of a fixed point for a non-expansive map. You can see that it's quite different. Not difficult, but different. And you just cannot have this result for any general metric space. You require some additional geometric structure. In this case, you require the Kappa structure. Okay, so this is how you get the existence of a fixed point of a non-expansive map in this space. And I think we will have a short break, maybe like 5 minutes, and then after that I will elaborate more on this topic. See you in 5 minutes. Okay, before I go further from this result, I will just give you a reference to this. So the theorem was given by Kirk in 2003 and 2004. There are two seminal papers published in the proceedings. Truthfully, difficult to find the full paper of these. But okay, so the first paper in 2003, it was a proceedings of a conference in Sevilla, Spain. And that was the first time that fixed point theory was introduced in Cat0 space. So the 2003 paper was in Cat0 space. And a year later, he extended it into a Cat Kappa space. Now the problem can happen when you think of some reasonable examples of these maps. Okay, we don't talk about the contraction because that's for general metric space. Okay, and that 99 years of this has proved that it is a useful result. But coming to this. Okay, so we talk about non-expansive maps in Cat0 space and in Cat Kappa space when Kappa is positive. Are these results useful? So what are the good examples for a non-expansive maps in this kind of space? Okay, you can talk about rotations, why not? But we don't want to only apply to rotations. As you see, that rotation breaks many rules. There is a very important class in Cat0 space that is non-expansive, where we call the proximal maps, or more generally the resolvence operators. Okay, that are non-expansive. But that only holds true when kappa equals to 0. If you extend to kappa positive, then the resolvents, the proximals, the projections, and so on are no longer be non-expansive, and then the problem comes in. Okay. Up to now, I do not know a good example of non-expansive mapping in kappa space when kappa is positive. Okay, the result is there, but what are the good examples for non-expansive maps when kappa is positive? Okay, many of my colleagues have been working on these problems, and they also have a thought that maybe non-expansivity is not really a good fit for the case kappa positive. Okay, but we still talk about proximals, we still talk about projections on kappa positive space, and to tackle these kind of problems we need to incorporate different tools, different techniques. Okay, so you don't use non-expansivity there. Okay, when you use non-expansivity, it's only for the case in kappa equals to 0 or less than 0. But when kappa is positive, non-expansivity is not a good tool, not so useful. So for the rest of this course, I will talk mainly about cat 0 space, but let me before we go to there, let me talk about projections or proximal maps a little bit. I think this is the first example for today. And what we are going to talk about in this example is the class of proximal maps. So I suppose, okay, X is the same, X is cat kappa for now. And I suppose that F is defined on X into minus infinity to plus infinity. Suppose that this function is convex, proper, and lower semi-continuous. Then what do we have? Maybe this is not an example. This should be more of proposition. Then the map. What is the map? For any lambda positive, the function for any lambda and x, the function y map to fy plus 1 over 2 lambda distance of y to x squared. Okay, x is given, lambda is given, and y is the variable. So y appears here and here. So this function is strongly convex. Okay, strongly convex may be not so clear, but it is. Another thing is that it is lower semi-continuous because f here is lower semi-continuous. Distance is continuous, squared, continuous, so this is lower semi-continuous. And therefore, this function possesses a unique minimizer. Okay, so how do we write? This unique minimizer is denoted with prox at parameter lambda of function f at the point x. Okay, or in other words, we can also write it like this. We can define the prox f lambda x to be the argmin, okay, argmin of the function f at y plus 1 over 2 lambda distance of y x squared. And this is defined for any x in capital X. Okay, so this is called the proximal map. This is called the proximal map. Okay, so this is the first result of this proposition. This is the second. So moreover, if x is cat 0, then prox f lambda dot, okay, as a mapping is non-expansive. This is the main tool in modern convex analysis up to today. In Hilbert space, this is replaced with the norm squared. Okay, it's called the proximal operator or the proximal map of f, of the function f with parameter lambda. And if you know the proximal algorithm, it is defined based on this proximal operator. And if X happens to be a cat 0 space, then, okay, so this is defined for cat kappa space, okay? But when X is cat 0 space, then this prox operator or prox map is non-expansive. This is very important. When you go to kappa positive, you lose the non-expansivity of this prox map. That's very unfortunate. Let me give you an example. So if we put f equals to IC, the indicator function of the set C, with C being a subset of X, being non-empty, closed and convex, then you can see that prox of IC at any lambda is just the argmin of y in C of the distance from y to x squared, okay, with input x. Okay, come to this. Y f is IC, right? So if y belongs to the set C, then this disappear, it's 0, disappear. And if y does not belong to the set C, then this becomes plus infinity and cannot be a minimizer. So the minimizer can only live in the set C. So here, argmin of y in any x, in the set X, any y in the set X can be replaced with any y in the set C, because if y is outside of set C, then it cannot be a minimizer for sure. Okay, so and this reduced, and this is just a constant. So if you remove this constant, you rescale the function, but the minimizer still is the same. So if you take the proximal map to this proper over semi-continuous and convex function, then it just reduces to this, which is finding the closest point, finding the point y in C, which is the closest to the point X given here. And this is called the projection map onto the set C at the point X. Okay, so you can recover the projection map from the proximal map with the indicator function. So this is nothing if this is the set C, non-empty, closed, and convex. Here is X. So it's just the metric projection. Is the closest point on this set C that is, the closest point to X on the set C. And now we will show you that this projection will no longer be non-expansive in kappa positive. Remember that the projection is a special case of the proximal map. Therefore, if you can show that in the case kappa positive, if you can show that there is a projection onto a non-empty closed convex set C for which this is not non-expansive, then you can ensure that the larger class of procs will also not being non-expansive in general. Okay. Okay, so let's take a sphere S2. Okay, we only need a part of this, so I didn't complete the whole sphere. And you take any point X. Okay, you take a point X here. And then what do? You take an equator. Equator is a nickname. So what is this? This is X perp intersected with S2. Okay, so you come up with the equator. And then you take any 2 points on the equator. Let's call this U and V. Okay, you draw a geodesic connecting X to U. Okay, you will make a 90 degree here. And another one here, you will make another 90 degree here. You can see that the inner angle of triangles on the sphere can exceed pi radian or 180 degrees, because this is already 180. So okay, you have this, and then you shrink this down, let's say by half. Okay, maybe you can call this first one U tilt and V tilt, and I want to call this U and V. Okay, then you take the geodesic joining U and V. All right, and you consider this as a set C. Okay, now this red segment is the set C. So C here equals to the segment joining U and V. Then you go up by half again. Okay, what should we call these 2 points? Let's call it P and Q. No, not good. Y and Z. Okay, so this is a geodesic segment, right? This set C is a geodesic segment, so it is closed and it is convex. Of course, it's not empty. Now you project this point Y onto this set C. What you get is exactly the point U. Okay, so you project this down, it will go down the geodesic, and this point U is nothing else but the projection onto C of Y. Next, you project Z here down to this set C, and you will get the projection exactly the point V. So V here is nothing but the projection onto C of the point Z. Okay, now you compare the distance between Y and Z. So Y and Z can be joined by a geodesic. This is the shortest one. And U and V. Okay? So you compare the distance between the two. And you can see, visually, you can see that the distance between U and V, let's start with U and V. And U is the projection of Y, V is the projection of Z. So you have D of projection of Y, and V is the projection of Z. This is strictly larger than the distance between Y and Z. Okay, and now you can see that this is not a non-expansive map. Now you can see that it's not a non-expansive because projection is on the left-hand side. It is larger, strictly larger than the distance between Y and Z. Okay, non-expansive means on the left-hand side it has to be not larger than the right-hand side. But here you can find an example for which the distance on the left-hand side is strictly larger than D of Y and Z. Okay, so this is an example showing that you will lose the non-expansivity when you go to the positive curvature. Okay, so that's what can go wrong when the curvature bound above by kappa is positive. Okay, now let's come back to our paradise when kappa is less than or equals to 0. So what do we really want is that we want to recover the case of Banach's contraction principle. In Banach's contraction principle, you can approximate a fixed point by x0 and then tx0 and then t2 of x0 and so on. This is called the Picard sequence. You want this simple approximation, okay? In non-expansive, the results regarding the existence of fixed point of non-expansive map of Kirk, you can see that the proof is not so constructive. You just show that it exists, but okay, it's a weak limit of some sequence, but that sequence is not so practical. It's not as nice as the Picard sequence. So we want to come up with something simple and beautiful like the Picard sequence. And you can see using the rotation that non-expansive map does not work. I mean, if you apply the Picard sequence to the rotation, it will not work because it's non-expansive, but it's not what we call firmly non-expansive. It's just non-expansive, but not firmly. So to recover the nice behavior appeared in the Banach's contraction principle, we need a stronger version of non-expansivity. So here a map T define on x into x. Now I use x because in this definition we need geodesicity, and we will use it through the geodesic of a cat0 or cat kappa space. Okay, so a map T is called firmly non-expansive. If for any x, y in x and any t belongs to this interval, it holds for any x and y, the function t coming from the open interval 0 to 1 mapped to the distance between 1 minus tx plus tx and 1 minus ty plus ty is non-increasing. Okay, so this has to be non-increasing. Okay, non-increasing means when t is small, this value have to be less than or equals the value at t large. Okay, you substitute, let's say t1 here, you get one quantity, you substitute t2, which is larger than t1. The quantity that you get out of t2 will be at least, larger than or equals to the quantity that you get out of t1. Okay, therefore when you take limit as t tends to 0 and t tends to 1, that will imply that the mapping, which is firmly non-expansive, will always be non-expansive. Okay, because when you substitute t equals to 0, this is distance between tx and ty. When t equals to 1, you have the distance between tx and ty in the limit. Okay, so of course it is non-increasing, so when you take the limit as t vanishes and t goes to 1, you will get the monotonicity and you will get dtx ty less than or equals to dxy. So it's non-expansive. But this is more than non-expansive. So what is this? So you have any x and y. You map x into tx and you map y into ty, maybe here. Not forced to, but just to draw you some figure. And what is this? This is the, okay, when t travels from 0 to 1, this is the geodesic connecting x to the point tx. Okay, so you have x here connecting to tx and y here connecting to ty. And you compare the distance of this and this. Okay, so we don't compare when t equals to 0, but actually that's not really change anything. So you can change to closed interval if you want. It does not hurt. No effect. Okay. Okay, so when t equals to 0, this is the distance on the right hand side that you compute. And as t goes to 1, t equals to 1 is this distance. Okay. And as you move along with t from 0 to 1, you will kind of compute this kind of distance. Okay, it goes to this direction. And as you can see, the terminology is called the firmly non-expansive. So it's kind of firm shape, not fat like this. So it's firm. Okay, so we call this type of mapping firmly non-expansive. And what can we gain out of this firm non-expansiveness? Let me give you this proposition first because it will motivate you why do we need this firm non-expansiveness. Okay, the proposition is saying that if x is cat 0, f defined on x into extended real excluders minus infinity, this is convex, proper, lower semi-continuous, then what happens? If x is cat 0, f is convex proper lower semi-continuous, then prox of f, parameter lambda, is firmly non-expansive. For any lambda positive. Okay, so you can choose any lambda that you'd like. This prox operator will be firmly non-expansive, always. And this only holds true in a cat 0 space. So from this theorem onwards, we kind of don't want to talk about kappa positive. We just kind of abandon that difficulties for now. Okay, so x cat 0, f convex proper lower semi-continuous, then the prox operator is firmly non-expansive. Okay. And actually we have one more thing that maybe I forgot to tell you about. Okay, so please allow me to include it here. Okay, so moreover, the fixed point of this prox operator of f and lambda, the fixed point set of this is nothing else but the set of minimizer of f. Actually, for these two holes, we don't need cat 0 space, but just please allow me to write it here, okay? Since I don't have too much time, so I think the cat kappa space case might not be addressed in detail. Okay, so this proposition comes from, I have to note that even though the proximal algorithm in cat 0 space was introduced in 2013 by Miroslav Bashak, this prox operator itself was introduced much earlier for different purpose. They used this operator to study harmonic maps, to study gradient flows, and so on. And the results, these results was proved by Jürgen Jost in Leipzig This is in 1995. And independently by Mayer in 1998. But of course, independently, maybe during that time there were no internet, so getting to know every result in the world is kind of virtually impossible. So Mayer didn't know the existence of this proposition by the time he published this work. Okay, so they were developed independently. So now you see that the prox is firmly non-expansive, and one more thing is that the fixed point set of the prox operator is nothing else but the argmin of f, or the set of our minimizer of f. So what then? So that means if you can find a fixed point of prox operator, it's the same as you were being able to find a minimizer of f. Okay, using fixed point theory for firmly non-expansive map. Now comes the theorem. Okay, so if if X is a complete cat zero space C subset of X is non-empty, closed, and convex, T defined on C into C is firmly non-expansive, then for any x naught in C, the Picard sequence of course it is Tn of x naught is we need one more assumption, sorry. We need the assumption that the fixed point set is non-empty. Then I just realized, but I'm not sure what I wrote. When I talked about existence for a fixed point of non-expansive map, we need the boundedness of C, okay? I'm not sure I speak of that, but we need the boundedness of C. So C in that theorem have to be non-empty, closed, convex, and bounded. Okay, so if I did not remember what I wrote, but if I missed out the boundedness, please add that, okay? So we need the boundedness there. Okay, then the Picard sequence is weakly convergent to a fixed point of capital T. Okay, so this is the result that is very, very useful, and you can somehow retrieve what happens in the Picard's, what happens in the Banach's contraction principle. So you have X complete cat zero space, of course, C non-empty, closed, and convex T, self-mapping on C being firmly non-expansive, and it has a fixed point. Actually, if here you assume the boundedness on C, then the existence of fixed point comes for free. Okay, then what happens? Then for any x naught you define the Picard sequence similarly as in the Banach's contraction principle. This Picard sequence will weakly converge to a fixed point of T. Okay, what is difference between here and the Banach's contraction principle is that this Picard sequence will only converge weakly. You cannot hope for more, okay, because your map is not a contraction. This is the best that you get, okay. In Banach's contraction principle, you have the strong convergence, which is of course better, but here you don't have a contraction, you have only a firm non-expansiveness, and this is the best that you can hope for. Of course, if you assume that X or C is locally compact, then of course the weak convergence will turn into a strong convergence. But when you keep in mind, when you assume the local compactness, that means you are working in finite dimensional space, more or less. Okay. Okay, so in this theorem you have a way to construct a fixed point of a firmly non-expansive map. And as you can see in this example, no, not example, in this proposition, that the prox is firmly non-expansive. So you can replace this T by this prox, okay? Of course, fixed point non-empty means you need this argmin, you need the function to has a minimizer, at least one. Then you can repeat this prox operator and you will be weakly convergent to one of the minimizer of F. Okay, so that is one application. The next question comes when I ask, okay, what happened when this prox turns out to be a projection? As you know, one specific case of the prox is the projection. And what happens when this prox is a projection? So let me write it here, and you will see that it's not so pleasant. Of course, you can apply, but you will see that if the prox reduces to a projection, it doesn't really make sense to use. So you start with x naught, anything, and then you, okay, let me write the prox first. Okay, you call this x1, and then from this step you compute prox again. Let me call it the prox of x1, and this is x2, and so on. And applying this prox iteratively, you will converge to a minimizer of F. Now what happens if this prox is a projection? So suppose C here is a non-empty closed convex set. Okay, so the fixed point of projections is exactly the points on C, because the distance let me write here. So what does it mean? It means that if you project X onto the set C and it returns you X, that means X is already in C. So if X is outside of C, the projection cannot be X itself because X is outside of C. The projection is the closest point on C to the point X. So the fixed point of the projection is exactly the set C, okay? Fixed point of projection onto C is exactly C. And when you apply this kind of result, it means you want to find a point in C. C may be defined very abstractly, maybe like if you are in a function space, C can be a set containing functions satisfying a list of properties, and maybe you don't know an element inside that set. You just know that it's non-empty, closed, and convex by some proofs. So you take any function and then you project. But unfortunately, because C is complicated, you don't know elements in C. What it implies is that if C is very complicated, the projection onto C is even more complicated, right? So computing this is not practical if C is complicated. And if you apply projection here, that means you want to find a point in C. But if C is complicated, projection is cannot be computed. Okay, that's the first issue. The second issue, if C is simple, if C is not so complicated, this will end in the first iteration. You want to find a point in C, you project onto C, you get the solution. Okay, so no use here. Therefore, when prox reduces to projection, that will not be so satisfying in practice. So what happens when you want to find a point in C? One possibility is that the set C can be expressed as an intersection of our closed convex sets. Of course, intersection of closed sets is closed, intersection of convex set is convex, then this C is closed and convex. And what is the problem here? You want to find a point in C, but you don't know what C is. You just know that, okay, C is the point for which, suppose, for example, C1 is a set of points of X such that Px is true, P1x is true, and C2, P2 is true. So Ci can be maybe some statement Pi is true. So this is kind of a list of statements, list of properties that you want, and you kind of want to find a point that satisfies all the properties given by C1 to CR. Okay? Suppose that projection onto each Ci's are not too difficult to find, but when taking the intersection, this is weird. This is just like difficult. So we break this C out into the intersection of our sets, our closed and convex sets. And what happened when we want to find the intersection here? Okay, this is the case where the projection onto the set C is not so simple, it's complicated. So instead of doing this, we want to kind of project onto C1 one time, and then for the second time you project that result onto C2 and onto C3 and so on onto CR. Okay, one at a time, but finally you wish that you will reach a point in the intersection. This is very intuitive, and this result was first studied by John von Neumann. Okay, so you have kind of x0, this is C1, this is C2, and you want to find a point somewhere here. Okay, so suppose C1 is a ball, C2 is a ball, the intersection is not the ball. So the intersection here, you don't know how to project onto this, but you know how to project onto a ball, right? Because you can just take a center and then draw a line and take a point here. So that's very simple. So you can take a projection here onto C1 and then onto C2. Okay, and you repeat, you will be oscillating into this, towards this point in the intersection. Okay, so this is the idea. So you start somewhere, you project onto C1, then C2, then C1, and C2. Alternatively, you will get to the point in the intersection finally. This is the idea. Okay, so the result here was proved by Espinola. No, I don't think so. Arisa Ruiz, I think. Yes, Arisa Ruiz. Lewisten. Luis Tian. And Lopez in 2014. And then we can make a progress from that result from 2014. It says like this: if X is a complete cat zero space, C is again non-empty, closed, and convex. And now you have the maps T1, T2, up to TR, maps from C into itself being firmly non-expansive. And one more thing is that the common fixed point, which is the intersection of the fixed point set of each of the maps, is non-empty. Let me call this F, capital F, okay? Then what do we get? Then for each x naught in C, the Picard sequence given by this, given by TR composed with TR minus 1, and so on until you reach T1. You iterate over this composition at the point x naught. Okay, so this is a big sequence here. Is weakly convergent to a point in F. What is F? F is this common fixed point set. Okay, so this is a great improvement from the previous result, and this was proved by whom? Okay, so Arisa Ruiz again. Lopez and Nicolay in the following year, 2015. So what happens here? You have this composition of firmly non-expansive maps. You keep iterating on this composition at the point x naught. Okay, this is a sequence on n. I write n here because there are so many parameters. You have 0, you have n, and you have r. So to clarify that this is a sequence in n, I just write n here. Maybe like this. Okay, so this will weakly converge to a point in this intersection right? This now makes sense because what exactly are you doing? You first take a point x0 and then you plug into T1, and after T1 you plug this T1 x0 into T2, and then you plug this result into T3, T4, and so on until you reach TR. You complete one cycle. And then you have this kind of composition at x0, and then you put that result into T1 again, and then to T2, T3 until you reach TR. That completes the second cycle, and you keep iterating like this. So what actually happened is that you apply this x0 inside each maps one at a time. Okay? Now imagine that T1 up to TR are the projections onto, so C1 here will corresponds to a projection onto C1, C2 here corresponds to a projection onto C2, and so on until CR you got a projection onto CR. Okay? So now you imagine that T1 up to TR are defined by these projections. Okay? And you can apply the point x0 into one projection at a time. So if each CIs are projection friendly, so that means you can project a point onto each of these with ease, then computing one projection at a time is not a pain. Okay? If you compute the projection onto the intersection, that might be hard. But well, you can project one at a time, and you expect for the convergence that I just drew to you earlier. So what happened? It will converge, right? This will converge to the intersection of fixed point of each projection. So what is that? I will write it here. So the intersection of fixed point of the projection onto CI, okay, where I equals to 1 to R. So what is this? The fixed point of projection of CI, this is exactly CI, right? I wrote it somewhere. No. I wrote it, but I think I erased it. Okay, so the fixed point set of the projection onto CI is just CI. So this is essentially the intersection 1 to R of CI. So what happened here? You keep doing the projection cyclically, one at a time. You will reach a point in this intersection, which is the set C that you want. Okay, and this is how you can come up with a solution of a convex feasibility problem, which is one of the problems that has been studied extensively in convex analysis, but this is in the setting of a cat-zero space. And as expected, I have no time to talk about the case where kappa is positive. So just to give you a very quick comment, when kappa is positive, you lose all the non-expansivity. So what we are going to use there is the stronger version of quasi-non-expansivity. Okay, we can build a stronger version of quasi-non-expansiveness, and finally somehow come up with the result which resembles the results of Arisa Ruiz, Lopez, and Nicolay in 2015. The results in kappa space that I'm talking about right now is one of the work that I have been doing with one of my PhD students and a colleague in Japan, Fumiyaki Kosaka. Okay, so hope you find some interesting things today, and I think I will just finish for today, where we talk about fixed point theory and how to apply them to solve some problems in convex analysis. For tomorrow, we will talk about the first order theory of convex functions. Okay, see you tomorrow, and have a good day, have a good night, whatever. See you.